How does the Cu.56Ni.44 PBA material demonstrate its rate performance, and what specific experimental conditions are used to evaluate how quickly it can charge and discharge under different current densities? And in what ways do its intrinsic structural characteristics, such as the synergistic interaction between copper and nickel within the Prussian blue analog framework, contribute to rapid ion diffusion and minimal ohmic resistance during high-rate cycling? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How are the charge/discharge curves analyzed to determine the capacity retention at elevated C rates, and what mechanisms facilitate the efficient electron transport and ion migration in this material during fast electrochemical processes? How does the observed rate performance compare with that of other PBAs or similar cathode materials, and what insights can be drawn from its voltage profiles regarding polarization effects or kinetic limitations? Moreover, how does the Cu.56Ni.44 PBA material perform in terms of cycle performance? And what factors underlie its ability to maintain either a prolonged or stable capacity over hundreds or even thousands of cycles without significant degradation, and what specific tests or metrics, such as Coulombic efficiency, potential shift analysis, or structural integrity assessments, are employed to quantify its long-term cycling durability? In what ways do its microstructural features and interface properties between the electrode and electrolyte help sustain a high capacity retention over many cycles? And how might the incorporation of both copper and nickel alter the redox behavior at the molecular level to mitigate common issues like lattice distortion or phase degradation during repeated ion intercalation and deintercalation? Furthermore, how do these performance indicators of rate capability and cycling stability provide guidance for further material modifications or optimization strategies to enhance its practical application in high-performance battery systems? And what additional investigations could be pursued to fully elucidate the relationship between composition, structure, and electrochemical behavior in order to drive advancements in the design of next-generation cathode materials? How do the Ni-Fe PBA and Cu-Fe PBA materials, despite exhibiting high rate capability and excellent cycle stability, fall short by being sodium poor when not charged? And what are the implications of the sodium deficiency for matching with traditional sodium-free anodes in the construction of practical sodium-ion batteries? And in what ways does this challenge prompt a rethinking of material composition for such energy storage systems?